POPL'18, and here I'm going to talk about our work, the analytical modeling of cache behaviors for affine programs. Cache is a critical component in modern processors, and it's gap speed between processor and memory, and so its evaluation is deserved to study well. So here is a basic organization of cache. Basically, here it shows two cache sites with two lines for each site, and given address, you have tag bits and the set index bit in the middle, and also the block offset bits. So basically, it works like you will select the cache site based on the set index bit, and then you will compare each tag within the cache set and to find its match. If not, it will be a miss. If it is a match, then you will check the value bit to see if the data you want is in the cache. So this is basically how a cache and its addressing works. So basically here I'm going to use the simple loop nest example to demonstrate the ordered cache behaviors. So basically this simple example, so here's the basically execution orders. Basically it will read the right hand side array element and write to the left hand side array elements. Basically, the register is not affect the cache behavior, so basically it can be omitted. So the program that we're gonna analyze for the cache behavior looks like this. So basically, it's read two elements and write to another array element. So for a given cache configuration, for example, a single level two-way set associated cache with its size and cache line listed there. For a double array, basically, it's one line takes one element here. So then here is the instant and traces means the iteration point, which is I and j equals 0, which is the first iteration point of the loop nest, and then shows the cache state for set 0 and set 1, which is basically the cache set content after execute the trace on the left. And then there's on the rightmost hand side is the cache hit or miss status. Basically, when you execute the first iteration point, which is 0, 0, it will basically read A01 and 1, 0 and write to 0, 0. Basically, the cache set 0 and 1 will hold the content of the array cells after it read. For example, the first read, cache set 1 will hold the A01. And since these all are the first access to the cache line, then it without a code miss. Then for the next iteration point, you again perform 2 read and 1 write. So for the read A02 is basically will map to the set 0. It will going to evict the previous A01 within the cache size 0 and without a cache miss. And for the write to A01, it will hit the cache set 1, which the data is already there, so it without a cache hit. And then the trace continues, so the status continues. So as we can see that to model the cache behaviors, the ordered list of cache events including the read and write to the event to the cache lines, and also the code misses that when the address line is first accessed, and other misses including the capacity misses and conflict misses. And a dirty eviction happens that the data in the cache line is replaced and it's marked as dirty, and it will write back to the next level cache when it gets evicted. And also the cache state at any point within the program execution. And so it's basically think about case that it's a mixture of a affine program and non-affine program. You will need to want to model the cache state after the affine program. And so the previous existing cache modeling approaches, the first is cache miss equations. Basically, it counts the cache misses for a perfectly nested loop programs and for a single level cache. and it's generate the cache miss count basically by solving the cache miss equations it generated. And another approach is the cache modeling, which provide a closed form solution for polyhedral program for a single level caches. Basically, it's also only generate the cache miss numbers. So the need for for modeling cache behaviors is of the ordered cache event, is that with the ordered sequential cache event, you can generate, like, you can modeling the hierarchical caches, which require the cache sequential accesses for this level and for the next level. And with this order set, you can perform the bottling of the worst case execution time, and also optimizing the cache design analysis, and also determine the array padding stats to reduce the conflict misses. And for the purpose of analyzing the cache vulnerability, you need the exact order events for the cache key, cache miss, and evictions, and such as this ordered cache event. You have to get this kind of information to perform this cache vulnerability analysis. So as we can see that the purpose of to generate this order set is important, and it can be enable many of the analysis in the future work. So the key contribution, the key ideas of our approach is basically to generate the exact sequence for affine programs with given cache configurations. And we will incrementally show that we will compute the cache behaviors for the set associated cache. And we also, we can stack the cache accesses for the next level cache, which is hierarchical caches. So basically, we are not simply counting the cache misses as previous work, but we still have some limitations. We basically assume the virtual index memory addresses, and the execution time, as we will see later, is depend on the generated side. So here I want to use a simple program as listed before to show how our formulation works and how it models the cache event and cache behaviors. So basically, for this loop nest, the program domain will be the constraint for these iterators with a simple set, and the read and write references will be a simple relation from a statement to array indices, to array cells, which is then the statement to references relation will be the union of this read and write. Another thing important is the program execution order, which is a relation from statement to the time point. Basically, it's mapped from a statement, for example, S1 to the time point for this program execution in execution order. So the program order is only like the execution order of basically it can be treated as a trace, and then the interaction with the program domain will bound these relations so that you can count the numbers and do something else. So another important relation to reason about the program order is the lexicographically success time point. So basically, this relation is from one time point to future time point, which is lexicographically later accessed. And similarly, you can get the lexical success equal, which means including this time point itself. So since now we have the program space, we have the information from the program, and now let's see the memory space. Basically here for the simple program for a double matrix, and we basically get the memory space by linearize the array itself. Basically, we calculate the linear address based on the start, means the start address, memory address for this array. And we linearize the indices, and we times the offset. So basically, this get the relation from a reference to the memory address it maps to. And now we have the memory space relations and the program space, and now it's a cache space, which is basically we have a relation we will map the relation from memory addresses to the cache line and cache set that this memory address belongs to. So which is basically this relation, the address to cache line, which is basically to divide the block size, which is used to find the cache line it maps to. And similarly, you can get the cache site. Basically, you have basically you need to get the modulo of the number of set. Then you can have the map from the cache line to cache set. Now with all the information before, we have the program space information, we have the memory space information, and also the cache space information. And now we can build a relation from the program to the cache information space itself. So basically, we will composite relation from the state to reference, and reference to address, and address to cache line. So basically, this is a relation from the cache, from the program statement to the cache line that this statement maps to. Similarly, you can get the cache set that this statement maps to by composing another relation, which is the line to set relation. And so, for example, the previous work on the distinct cache line model can be expressed using our formulation in a more compatible way, which is the statement to time map reverse, which is basically the time to statement, and the composite with statement to line, which is basically the time point to the line accessed for this program. And the range, you will get all the distinct cache line accessed by this program. As here you can see that this is a more compact expression compared to previous work. And so note that the formulation can be also written in terms of time, so that the other statement can be considered simultaneously. So basically, to transfer the statement, map the statement to the time point that it maps to, basically you have the relation from the statement to time reverse and the composition with the statement to time. Then you will get the relation from the time point to the cache line. So similarly, we will get the relation to the cache site. So as now we have the formulation here, so to model the cache misses for a program, we have the two classes of cache misses. The first class is code misses, and the second class is the capacity and conflict misses. So for the code misses, the first access to any cache line in the program that maps to will result in a code miss, which is basically can be expressed in a way like the line to the time point that it's mapped, this cache line mapped to. The lex min means the first time that this line accessed, and composite with the time to statement, which give you the statement that this line first accesses the cache line, and the range will give you the number of this statement that will result in a code miss. So here, as we already get the code misses, the next step is to get the conflict misses and the capacity misses. Before that, we want to see how we model the access to the same cache line. So as seen in the figure, all the colored point are the time point which access the same line. The third point is let's consider the third time point, which is in gray. And the previous black is access the same line, and also for the following. So to get the same line that access later, we can basically have a composition of the time to line and line to time, which is basically you get all the colored time point which access the same line, and then you intersect with the lexical successor point, which is basically showing as later. It will basically remove the previous point that happens lexicographically before the gray point as shown in the third one. So basically, the yellow and the gray point is the same line success point, which can be obtained by this formulation. Similarly, you can get the same line success equal, which include itself, and also for the point which you can get the same set. So now let's see the cache misses for direct map caches, which this can be So let's see the figure. So all the colored point again is access the same set, and the later green ones is access the same cache line as for the first time point. And then how to map the cache misses, we need to basically remove all the, we basically need to count all the time point that access the same set, but before it maps to the same cache line as in the green one. So basically we will have the same line success relation composition with the happens later, which means the gray point shows the same line, and subtract from the same set success, which is all the colored point. Basically, then you will get the cache miss for direct map cache. One thing to note that the same set success is a superset of the same line success relation. And now to how to model that the k-way associative cache is from the from direct map cache. We will need the cache misses except the order sequence for the k-1 associative cache. So here it just shows a list of time sequence, and all the black point is showing that they are accessing the same cache site, and the label shows that which cache line that it maps to. So to map the from the k-1 associativity to k-way associativity, we just reserve one more slot for the miss, and we will obtain the next miss after this reserved time slot, which will result in a cache miss. Basically, for here, this is a k-1 associativity, so the next time slot for the miss will be L7. And together with all the following accesses to the same cache line will be removed. And then the remaining part will result in the misses for the k-way associativity. This can be expressed in the formulation as this. We will have the miss for the k-1 associativity, and the lex min will get you the L7 point, and the composition with the same line success and equal, you will get the 2 L7 black point, and subtract from this cache k-1 associativity, then you will get k-way associativity cache misses. And also for the dirty evictions, that we also model that cache event that which the details can be shown later in the which can be details in the paper. Sorry. And so the way how to model hierarchical caches is basically you need the cache read, and you need the read and write event for the next level cache. So basically the read for the next level cache is basically the read misses from the current level, and the write to the next level is the write misses plus the dirty eviction as mentioned above from the current level. And then it can, with this read and write, then you can start model as the similar process as I described above to model the next level cache misses and its behaviors. And there are other details with write allocation policies and also cache state, and you can refer the paper for more details. And we basically have a implementation of the approach which is called polycache, and we tested it by a lot of plenty of benchmarks, and also our test could be in a parallel way, which basically assign each process for the simulation for the analysis of each cache site, which basically can you can accelerate your analysis process. And there's plenty results that show in paper you can refer to. Basically, we achieved the perfect accuracy match between between a trace-based simulator and for the virtual index LRU cache for red allocate policy. And time complexity, it depends on the irregularity of the generated set that you will generate. It's basically, if you it's very hard to predict that how long it's going to take. But in practice, we will see that it's much faster than the cache simulator. And plus, we also have many acceleration techniques. When the time happens to be very long, then we can execute the approximation approach, which accelerates the analysis process. So the take-home message will be that the static analysis for the cache misses is possible for affine programs, and as in our approach, we generate other set of accesses that result in a cache miss, and we also this can be modeled the cache hit and other behaviors. So compared to previous approach, our modeling can be extended, and for many future works, as mentioned before, for the vulnerability analysis and worst case execution time analysis. So the compile time analysis is possible, but potentially it's sometimes it's cost, but it works quite good for many practical cases. Thank you.
One question maybe, as I understand. Oh, you want to start there? Sorry.
Okay, the first anonymous question is how and where we incorporate this in existing compiler framework like LLVM. There are interesting interactions with instruction scheduling as well as register allocation. Okay, I'll let you read it as I read down. How and where can we incorporate this in an existing compiler framework like LLVM? There are interesting interactions with instruction scheduling as well as register allocation.
Actually, this can be incorporated with the LLVM because it's in our work we utilize a tool which is called PAT, which is depend on the LLVM and to extract the program, and then we use an integer set library to use that, so it's easy to incorporate with LLVM. But for register allocation, we currently haven't think about that. Maybe it's counted as future work later.
And then one more. Okay. The next question, he decided not to remain anonymous by Matt, is can we extend this framework? Let me read it. Can we extend this framework to model MLP, which is memory level parallelism, to account for the fact that not cache misses are equal? Not all cache misses are equal, but only the ones where the latencies are not hidden or overlapped with the other memory accesses?
Basically, we have a future work in mind that we will basically to extend our analysis on the simple parallel programs that it's not like simple solution directly that can be applied. So if he's interested, we can talk offline after. Yeah.
So how expensive is your analysis?
Okay, so here comes the. So here basically comes the time complexity, which is also listed in the paper. Here we choose two representative cases where one is cost more and one is cost very less and the other costs more. As we can see, basically these two benchmarks are very similar. It's basically sort of matrix multiplication, but you can see that analysis time is quite different. And here we break down all the integer set operations we use in our formulation. As we can see, most of them are cost really less, but you can observe for the difference and the coalesce that cost explode for the SIM benchmarks. That is because the implementation within the integer set library, how they perform the difference and how they perform the coalescing.
Mm-hmm. But all these programs are very short, right? So if you feed these programs here in these benchmarks, they're relatively short, right?
Yeah.
So if you feed a program with 500 lines of code,
this program are short, but the size are not like short. Basically, if you view them as a program traces, it's much longer. And also, basically this kind of affine program, when you perform like a affine transformation, it can extend it to 100 and even 1,000 lines code, as long as actually the analysis is not dependent on the code size, it's not dependent on the program size. It's basically dependent on the shape of the generated set you're going to perform. Like for example, you want to do the cardinality of the generated set. Basically, you're going to count how many shapes within the integer point. Is right. So if you have many small pieces with your generated set, then it takes more time for this integer set library implementation to generate your number. Mm-hmm. But if, for example, you could have even a very large program, but then the generated shape is like very in a good shape, then it's very fast. You will get a result. Mm-hmm. And to our best knowledge, is not possible right now to predict the shape that you generated, to predict how long it's going to take. So basically, we introduce a timeout mechanism to invoke a approximation if it takes long.
Maybe did you try some larger programs or only the short ones? I mean, I understand what you're saying, right? But did you try some real-world code on image processing or something that as a benchmark?
Right now, I remember. Right now, we only test with this polybench benchmark, and we could test with larger programs later. Yes.